Okay, let's quickly recall what we did last time, right? So what we did, and we also kind of gave a plan in the end, but so we start this game with an alphabet. So we fix this alphabet A. So for example, we can always think of B. So this is just 0 and 1. So this alphabet is basically symbols we can use. So if we think of B, we're considering strings. And then this, as soon as you do this, as soon as you fix this, this fixes your universe of B star. So what was B star? B star basically was all finite strings. So strings meaning zeros and ones strings, so somehow. And plus also you have the empty string there, so this is a horrible writing, but whatever. So B star is all possible strings, also including the empty thing. So the empty word, that is an empty string. And so you have this is all strings, and then inside there you had this languages, let's say L1, this L2, like, I don't know, L3. So when you specify some subset of B star, so all possible subsets of B star are all of them are languages. This is a huge class, but then you specify some of them in some way. We talked about their certain languages, so maybe write it. So we wrote down that certain languages are regular, so to speak. Right? And we had this definition of a regular language, which was, just to quickly remind you, you start out with just letters and the empty word, and if you can take their union, you can concatenate them, and you can take star, and you get regular languages. And we also talked about the intuition that these languages really are problems, so we try to classify all possible problems somehow. And computer science is nothing but trying to solve some problems, right? Also mathematics. But anyway, so we have this setup here that when we have this alphabet, not B star only, but also any kind of alphabet. So you look at the universe and you consider all the subsets, and you think of them as languages. And we have a special class there. Let's call, I don't know, let's draw this class maybe. Maybe in red. So let's draw. So there's this subclass here, maybe this guy's, right? So somehow this L3 is neither here nor there, but anyways, there's a subclass here, which is like a regular languages, right? So languages here, we call them regular. So by the way, we do not know as of yet whether there is anything that is not regular. We saw that some languages are regular, like natural numbers. We saw over some specific alphabet. We saw that letters themselves, the subset of letters is regular. We also saw that. We saw the variables are regular. So there exist regular languages. We know this. But we do not know whether there exists something that is not regular. It seems non-trivial to us to actually think about this problem. So anyways, now what I'm going to do is I'm going to describe regular languages in a different way. So this was somehow, let's call it maybe mathematical description, right? That you start with some things and then you build them with union, star, and concatenation. So let's give more computer science a description of languages, and then we will prove that this different descriptions that I would give you also describes the same red class here of regular languages. So what is this different description that I'm talking about? You all are aware of, I don't know if you remember or not, of this thing called Deterministic Finite Automaton. So if we think about, so deterministic, finite. So in short, this was called DFA, if you remember. We had this last semester, but if you don't know what this is, we will just cover it from scratch. But let's just, for the intuition, let's say you remember what this is. So this was something like, so I will draw a DFA and you tell me what things does this accept. So it starts like here. so let's call it, I don't know, Z0. Then it goes here. I don't know, then it goes here. Then it comes back here. And then I will circle it the second time. If you remember, this is also a start state and also an accepting state. And now I have to tell you what are the things that are coming in, right? So I'm telling you that the alphabet, that things that come in, can only consist of ones. So the things that come in are just strings of ones. There's no zero, let's say. And so then this is my DFA. So when it sees one, it goes here. Then when it sees one, it goes here. When it sees one, it goes here. So now I am asking a question. Which strings does this thing accept?
1, 1, 1.
So empty string, if we think about the empty string, it starts out here, so empty thing would be accepted, but let's ignore this for a moment. Maybe let's write down. So this is how I'm gonna, so let's call this machine M. So M is the name of this machine. Maybe some kind of different notation so it doesn't look like a state. So M is the name of this machine, and I will write LM to represent all strings that this machine accepts. Okay, so in this case, of course, what strings? I mean, 0 is not there. Somehow these are the strings over the alphabet A. So I'm using this. So the only letter I can use is 1. And you're telling me that it accepts nothing, let's say. It accepts 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on. So in general, it accepts things like 1, 1, 1 to the power I, where I is 3 times k, right? Where k is like a natural number or 0. So this is just a different way to write this. 1, 1, 1 to the power I means they are just written, it's concatenation power. So you understand the notation here, right? So 1, 1. So when I is 1, you get 1, 1, 1. When I is 2, you get 1, 1, 1, 1, 1, 1. Right? So it's a concatenation power. I equals 3 means you have 9 ones. So the language that this thing accepts will consist of these things. So multiples of 3 ones, so to speak, and nothing else. Is that correct? Somehow intuitively clear that if you have a bunch of ones, so this is, by the way, it's called a unary language. So there's no zeros, there's just ones. So all the languages over the alphabet 1 is called unary. So it only accepts those unary strings which are multiples of 3. What I'm going to prove today is this, that this is some kind of, so by the way, this here, L of M, is a subset of A star, right? A star is just all possible ways you can write ones. So it's like epsilon 1, 1, 1, 1, 1, 1, 1, 1. So all the possible ones, and it's a subset here, specifically those ones that are powers of 3. And what I'm claiming here that this language is regular, because I can construct a DFA that accepts it. And I will prove the otherwise as well, that if I can construct a DFA that accepts it, it's regular, and the other way around, if it is regular, then I can construct a DFA that accepts it. So this gives a new definition of a regular language. Regular language are those languages for which you can construct a DFA. So by the way, let's go back to intuition. What is a DFA, right? DFA takes string as an input, string consisting of some alphabet, let's say zeros and ones. If it's alphabet is 0 and 1, it just takes string of zeros and ones. So it starts with a string and it tells you the answer yes or no. So it's a decision problem. Remember when we had the example when I talked about in the last lecture about the prime numbers? So you can define a language. So let's make it more formal. Let A be now B, which is 0 and 1. And let's define language, I don't know, prime. This consists of strings. So L prime is a subset of B star again. So it consists of strings such that when you compute, when you realize this string as a binary number, every string can be seen as a binary number, right? If it starts with zeros, you ignore it or whatever. You can view it as when you can realize it and compute the in binary, you can compute a natural number that it corresponds to. So like this, if this is prime. So this language now consists of strings that correspond to prime numbers. And somehow let's only take those strings which do not start with zeros. I take it back. So this is exactly those strings that correspond to prime numbers. Then I'm telling you, if you can construct a DFA that only accepts these strings and nothing else, those strings that are actually correspond to prime numbers, then you solved somehow a decision problem that tells you whether a number is prime or not. How would I do it? I will take the number, change it into a binary, feed it to my DFA, and if it goes to an accepting state, I just follow it, then it's a prime number. And actually, you probably, I don't know, you have code, if you have a DFA, it's really easy to code it in the computer. Right? So you can actually code this thing that it goes here, then do this, do this, do this, do this, do this, just follow it around. If something is here, here, or here, then you accept and say yes. So this, if you are able to do this, if this language were regular, which we do not know, then we would, by building a DFA, we would prove it. But anyway, this is just the intuition, like this is what I'm going to do. But in order to do this, so the theorem that I'm proposing that I have to prove now is that if your language is regular, you can build a DFA. If you build a DFA that accepts it, then you can prove that it's regular from the mathematical definition. So this is the theorem that I have to prove. But first of all, in order to actually do this, I have to mathematically construct what is a DFA. Okay, it's nice to draw circles and arrows, but somehow, in order to prove something, you really have to construct the thing. So let me just write it down. Let's just look at this DFA one more time and see what it is. So what is this DFA? This is the question now. I hate this color. Let's go to red. So what is this? What does this DFA consist of? What is the data that I have here? Let me start. First of all, I'm telling you, it's I don't know, 5 things, I think. So I'm saying that this thing consists of 5 things. The first thing I have to specify, what are the possible inputs somehow? Because I know that 0 is never coming in, so I do not have to draw arrow where you go from here once you get 0. So first thing I have to specify is the alphabet itself. So I have to tell you what are the symbols that are coming in. Otherwise, you cannot draw the DFA because you have to make an arrow for every possible symbol. So first thing is you have to specify the alphabet. What is the second thing I have to specify? If I'm constructing this DFA, I have to tell you what are the states. So here I would specify, in this case, I will tell you I have 3 states, Z0, Z1, and Z2. So I told you my alphabet was A. Basically, I have to tell you that this is 1. But somehow, let's write it this way so we know that this specifies an alphabet. So I told you an alphabet. I told you that there are 3 states. Okay, then I have to tell you which is the start state, right? Because I indicate with a special arrow which of these guys which is the place where I start. So basically I have to tell you which one of these Z0, Z1, and Z2 is the start place. So I write Z0. So let's say this is start. So it starts at Z0. What else do I have to tell you? Of course, the accepting states. This can be, by the way, you can have couple accepting states. It doesn't have to be just one state where it ends. You can have many ending states or accepting states, and if you end in any one of them, you say that it's accepted. So accepting states, let's call it ZE, is actually a subset of Let's write it. I don't know how to. So it is a subset. This accepting state is a subset of Z. This is Z, by the way. And in our case, this is Z0 again. But in general, you have to specify which states are accepting, which state is the start state, what are the states, what is the alphabet, and what else? The most important.
Transitions?
Yeah. Where the arrows are going. I have to know that from Z0 I'm going to Z1, and from Z1 I'm going to Z2, and from Z2 I'm going back to Z0. This is your program. If you think of this as a very simplified computer, A is the strings your computer can read, the symbols it can manipulate. Z, somehow the states your computer can be in. Then where does it start? What do you call an accepting place? So what do you call that computation is somehow completed? And then I will call this guy delta, is the program that you write, that if I'm in Z0 and I read 1, go to Z1. So okay, what is this delta? Let's write it for our case here. I will write delta like this. So delta, if I take Z0, if I'm in Z0 and I read 1, I go to Z1. So this is just a way of writing these arrows. Now, if I'm in Z2 and I read 1, I go to Z0, and just one more arrow. So for each arrow, I have this law. Now, if I add Z1 and I read 1, I go to Z2. This is it. Now look, let's say you do not have this picture of DFA. Let's say I gave you this. You can draw your DFA, right? This is the same thing as your picture, basically. So you write, first you look at things your symbols. Okay, one. Now you have 3 states. So you draw. I have 3 states. Then you know where the start state is. So you have 3 states like this, right? From the second information here. Now I know the start state. So let's say here is the start state. Now I know the accepting states, it's just Z0. So this, you draw this again. And now you look at delta. Delta Z01 is Z1, so you draw here. Delta Z21 is Z0, so you draw here. And delta Z11 is Z2, so you draw it here. So it's the same thing as this one exactly. So if you have this picture, you can draw this, write out these 5 things, and if you have these 5 things, then you can draw the picture. This almost specifies your DFA. I will tell you why it's almost and not completely, but DFA is basically these 5 things. So you know your states, blah, 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 and this thing is usually called a transition function. So let's write this. This is called transition function. Why is it a function? So why is it a function? So we had delta Z01 was Z1, delta Z11 was Z2, and so on, whatever. Right? So I'm telling you this is a function. What is the domain of this function? It has 2 variables. First one and the second one. It operates on 2 things. It has to take 2 inputs to give you 1 output. What are these 2 inputs? Oh, exactly. So it's Z is the first input and alphabet is the second input. And what does it produce? Z, exactly. So this is the function. So when I'm describing a DFA, I'm telling you I have to give you a set, which is alphabet. I have to give you an element of the set. This is a start state. I have to give you subset of this set, which is end states. I have to give you, what else? I don't know what I listed. I'm missing one. What am I missing? Yeah, start state, end state. Oh, states themselves. I have to give you what Z is. You know what A is. And I have to give you a function that for every state and every alphabet letter, so this is the set then, all possible pairs, where first one is a set state and then second is an alphabet that assigns you another state. pay attention that this bends things like, you know, when you were drawing these things, and let's say your alphabet is B, so I'm considering a different machine. And let's say I have some state Z17, and I drew 1, and it goes to Z25, I don't know, and then it continues. You have to draw 0 as well. 0 must go somewhere. You cannot say that 0 just gets it stuck or something like that, because this function has to be defined for every state and every alphabet letter. So for every state and every alphabet letter, you have to have a new state. This is what a function means. Function in mathematics is defined on its domain completely. We do not consider undefined functions as of yet. So everything has to be defined. So this is what it is. So this is basically what is written here. Maybe somewhere here. Here. This is what it is. So it says, so a formal definition, a deterministic finite automaton, or DFA, is 5 things: Z, A, delta, Z, 0, Z, A. A is just a finite input tape or an alphabet. Z is finite set of states. This is why this guy is finite, because it's finite amount of states. You cannot have infinite amount of states. Finite set of states. You have a transition function that for each Z and A gives you another Z. You have an initial state and some set of accepting states. Okay? So now let me ask you a question here. Let's look at the DFA in a different way, actually. Let's look at the same thing in a different way. Let's not draw it as circles and arrows, rather let's draw it like input is written, let's say, on a tape, like this. So let's look at our machine again that only accepts triples of 1s. So the input contains just amount of 1s like this. So how many 1s is there? 1, 2, 3, 4, 5, 6, 7, 8 1s. And let's say your machine starts here. Let's draw our machine in this weird way. So this is our machine, and I know that my machine starts in state Z0, and it can go to only Z1 and Z2. Once it reads 1, in this picture, machine will go here, right? Think of it this way, and it goes to state Z1. It will read 1 again, it will go here somehow in state Z2. Now maybe I'm missing actually 1. So if it reads 1, it goes to Z1. So it starts somewhere here. So actually it already reads 1 in Z1. It reads in Z2, like let's draw it, and then in Z1 or 0. So okay, I had 0. Then it goes to Z1. Then it goes to Z2. And then it goes to Z0, and somehow this tape is read now. And if so let's say then it will go like, do the same thing, Z0, 1, 2, 0, 1, and it will not accept. But if I have 9 1s, it will read the last one, and here it will end in Z0, right? So let's say the tape ends here and there's a hashtag or whatever. So once it reads the tape, our machine will end in Z0 on a hashtag and Z0 in an accepting state, and I say that this tape was accepted. Okay, so let's say this is the weird description of a machine that I drew, the different way to draw it. But now I'm asking the question here. Is this machine allowed to go left if it's a DFA, or stay in the same place? It read 1 and it stayed in the same place and read 1 again. So maybe you think of it as, this is a weird question. Let's think about this machine here, which is the same guy. Somehow, it's not seen in here, but somehow, does this description in red here somehow describe how this machine operates? Right? If the alien were come down from from somewhere else, and they looked at this machine. Okay, it tells me what is the alphabet. It tells me number of sets, states. It tells me start state, end state, and it tells me a transition function. But where does it say that I have to apply the transition function and go to the next state somehow? This is nowhere written. Somehow that when I start at Z0 and I read 1, I have to go to wherever this guy is taking me, namely Z1, and then read the input. See what I mean? So there is some extra information that is not encoded in here. This is what I'm trying to say. Unless you know some other stuff and somebody explained you this is how this machine operates, that it goes from Z0 to Z1 according to delta, and then it goes from Z1 to Z2 according to delta, and you say that this is accepting whenever the input is finished, and when you finish is Z0, if they do not tell you this, you do not know that this is how it works. There is some extra information that I have to tell you that will specify how DFAs work in general. And that extra information is called the configuration. So good. So we have to now explain what a configuration is. Basically an extra information you would need to specify what DFA does in general. And once we know what is a configuration, this basically defines how DFAs work. And then specific DFA will be defined by these 5 things. So let me tell you what a configuration is. So configuration is basically this. So again, let's draw DFA this way somehow. You have this tape. And then you have this head that is here in some state ZK, I don't know. And if it's, let's say it's reading a binary input. So in this case, your alphabet A is actually B, which is 0, 1. So the input is 0, 1, and it's reading something here. Let's say it's in the middle of the computation. So it's not at the start, but there's this thing here, and it's in state ZK. The configuration is, imagine this thing is working in the room. So it's like a computer, and it's just looking at a single tape, and you just came into the room. And what you will see in that moment is the configuration. Specifically, what you will see is you will see that it's in the state ZK, and you will also see that it's reading 0, and this is the tape left somehow. We do not care the things it already read because it's not important anymore. Because these are in the past somehow for the DFA. It can never go back there. It can never go back to this square here, so it's already in the past. So configuration is ZK. I will give you more intuition now. It's ZK and things that are left to the right. So in this case, this would be 0, 1, 1, 0, 1, 1, 1, 0, 1. So this would be a configuration. What am I aiming at is that I'm telling you now that this completely determines what will happen next. I do not care whatever here. I do not care what bits are written here, but this configuration completely determines what happens next. Oh. So if this is my configuration here, let's say, the next configuration would be, it will read 0. So let me erase this. So this was ZK, right? Let's actually give it a number. So let's say it's in state 17. Let's write 17. And what would be the next configuration? The next configuration, in case of the DFA, it will have to go here. We want to model this, and it will be in some state Z. Let's call it X. So next configuration, I wrote it this way, but I usually write it this way to the right, but it's going down, so I wrote it this way. So let's say the next configuration is ZX, and it has to have 1, 1, 0, 1, 1, 1, 0, 1, right? Now you tell me what is ZX. Can you tell me exactly what Zx has to be?
Delta Z17 no.
Exactly. So it has to be delta Z17 0. I have this information, and now I'm telling you that what is the next configuration? The next configuration, I know the information coming from deltas, right? It's written in these 5 things. So what is the next configuration? The next configuration, I have to apply what happens if I have a drawing instead of these 5 things. If I have a drawing, I had Z17, this is Zx. So exactly what happens when I apply delta to Z17 and 0. So the next configuration is something like delta Z17 0 1 1 0 1 1 1 0 1. What is the next configuration? Yeah, again, delta of whatever this function is, which was the Zx. So delta Zx1. So this is, let's look at the slides now and see. Let's enlarge this, make it smaller. We don't have to go full screen. So what is a configuration? What are all possible configurations? All possible configurations start with a state, right? So we had Z17 and some string. So they always start with a state, and then they have some strings in the alphabet. So in this case, so let's say A is 0 1 again, then the configuration I was talking about is like, let's say Z17, and then there's a binary string here. So I can write it this way, Z17 and a string. So every configuration consists of one state and then some string. This is what it's written here, that configurations are different state string. It's basically what you see when you enter a room with the machine working. Now I define a relation. If you do not remember what the relation is from discrete structures, it's okay, never mind. So that assigns to every configuration the next configuration. And it's assigned exactly as you said. So if your configuration was some state Z and some string like this, right? This is your K. What is the next configuration? The next configuration is to the state you apply the first symbol, so delta ZW1, and everything else stays the same. So this defines the next configuration, right? So for me to define you the DFA, I have to tell you how do you go from a configuration to configuration. And how do you go? You look at the state, you look at the first letter, and you apply delta, which comes with the definition of DFA. So K prime is the next configuration of K. I will write it this way. If K is ZW1 WN, K prime is delta ZW1, and everything stays the same. In other notation, they also write if W1, W2, and so on, WN. If you just write it as W, then you know this, right? Head of W is W1, and tail of W is everything else. So W2, W3, and so on. So you can write it this way. K prime is DZ head of W, tail of W. This is just the notation for this thing and this thing. Okay. So now, if I define it this way, the question is the following. Does this now I'm telling you DFA is something that operates this way. Does this allow to go left?
No, but it allows to stay in place.
How does it allow to stay in place?
Because do we have to go from K to K prime? It's not specified that we have to.
Yeah, okay. Yeah, I have not said maybe what a computation is. That's why. A computation is a sequence, let's call it K1, K2, K3, K4, and so on. This is a computation. So computation now, by definition, is a sequence of configurations where each one is the next configuration of the previous one by this rule. Now I'm telling you, if I'm performing a computation by this definition on a DFA, am I allowed to stay in place? No, because the computation means that you are applying delta to the first one and then applying delta again to the first one. So somehow this definition also encapsulates how computation happens with the DFA. And so let me give you, here is the definition. A computation is a sequence like this, such that each ki is a ki plus 1 is the next computation to ki. Now, a computation of m started with word w is the following. What would be the... So let's go back here again. So let's look at what would be the start computation, the beginning, so k0. What happens in the beginning? In the beginning, your machine starts here and it's in the start state. Whatever you picked as your start state, it has to be in the start state, and all your tape has to be written here. So this is what it says here, basically. It says that the computation of m started with the word w is a computation k0, k1, kn, such that the first one starts with the start state, z0 is a start state, and all w is written on the tape. So it took your w as an input, means that it started in the start state and it took w as an input, and it has to end in some state, whatever this z prime is, and nothing should be left on the tape. So it read everything. So going back here, this is the start state, and the end state should be that this guy is here. So z whatever, I don't know, 17 again, let's say, and there is nothing here. So this is, I wrote hashtag, but this is empty now. This means that it read the whole tape. This is the definition of computation. You start with a start state, your input is written, and you read the whole input going to the right. Okay, so we finish in 9 minutes because we start. Yes, and now we will say that the computation is that my machine accepts w, that once we're finished in state z prime and everything is read, so remember z prime is this guy here, once everything is read, that z prime is an accepting state that I chose. And then now language LM accepted by my machine M is all those strings or all those words, such that when I start my computation on this word, do this computation by applying delta again and again and again, I end up in the end in the accepting computation. These are the words that this thing accepts. We just go back all the way to our example here. In our case, the LM was just this thing, the things that this thing accepts. We did nothing basically. You knew all this. We just really formalized it that mathematically, wrote it down, what a DFA is and what do I mean by going from arrow to an arrow. So this basically defines a DFA. You know how to visualize it. We know already how to do this. The start state you write this way, accepting state you write this way, transitions you write this way, and sometimes if you have in your alphabet A, B, C, D, E, F, G, you write that with comma like this. So for A and B you go here, and for everything else you go here. This is what it means when there's nothing written. But this is just a convention. And the Wolfgang claims that you have seen this. You have seen all this in hardware lab. DRAM controllers, you have seen this. But we also saw this in algorithm and data structures course. We saw the failure function automaton, which was the DFA. This is our example that we already discussed. But by the way, this also includes zeros now. Right, so this is a slightly different example. Let me give you So now let's take our B is 0, 1. And now let's draw our machine this way, again accepting state, like this, like this, like this, 1, 1, 1. And for zeros, it does this. So then this is Z1, Z2, Z3. Okay, what language does this accept? So it accepts something like this, right? If the sum of ones is 1 is a multiple of 3, then it accepts.
Also, we can have infinite zeros.
Infinite input is not allowed. Because
I mean, as many zeros as...
Yeah, as many zeros as we want, yeah. Infinite strings cannot be taken into this because the way I define the computation has to end with z prime and then epsilon somehow. Everything has to be read at some point. If it never stops, then it's something else. So this is in LM. So this is M again. How would I describe this with 5 things? I would describe it as B is my alphabet, Z1 is my, well, Z1, Z2, and Z3 is my set of states. Z1 is my accepting state. Z1 is a set, Z1 is my start state, Z1 is my accepting state, and I have delta. And I have to write out delta. How many deltas do I have to write down here? Yeah, that's right. For example, what is Z0, well, Z3, oh, come on. Z30, what is this? Z3. Exactly. So, I mean, it's easy to replicate something from here. And if you have deltas, you can draw. If you have a drawing, you can come up with deltas. So this is what it is. So here it's a shorthand writing of the same exact thing. Delta AX equals A if X is 0. So that means that it stays in the same state. The name of the states here are A, B, and C. So it stays in the same state if X is 0, and it moves to another state if X is 1. This is what it says. Okay, let's look at this machine here. What language does this accept? This is exactly the same thing as we had mode 3. This is mode 7. So the thing, by the way, let's go back here and let me show you. We'll be done in like 5 minutes. So let's go back to our machine here. See? Where was this? This machine here. We saw that this is this language. Now I'm asking a question. Is this language regular? So the regular language is something that I have to start with alphabet 1. It has to be created from taking unions of ones, concatenation of ones, and the Kleene star of those. So exactly. So 1 concatenated with 1 concatenated with 1 gives you this language, 1, 1, 1. So this is regular. So now if you take this 1, 1, 1 language and take a star, this is exactly what you get. So this language is regular. So this language here is exactly regular. So I build an automaton and I can see that this thing is regular. So as I said, our gist is the... So now I'm asking you this question. So this is the language. It contains, again, the alphabet is only just unary. I only write ones. But it contains ones, the number of ones, which are multiples of 7 times I plus 25j. What this means, for example, it contains 7 ones. It contains 14 ones. It contains 25 ones. It contains 7 plus 25, 32 ones. So whatever I take for I and j, including 0, I can plug it in, and that many ones are in there. But does this contain 8 ones? 8. No, because 8 cannot be written as 7 times I plus 25j, right? So it doesn't contain 8 ones. So it contains some of the ones and some of... Does this contain 51 ones? Should we a bit? Or maybe 125 and then 7s. Okay, does it contain 32 ones? Does this contain 39 ones? It's 125 and 2 7s. Right? So you can take 1 to the 7 times 2 plus 25 times 1. So it contains some ones and it doesn't contain the other ones. Now I'm telling you that this thing is regular. Why? Because 1 to the power 7, just 7 ones concatenated is regular. 1 to the power 25 is regular. Their union is regular, of course. This is the definition. And then their star is exactly this. 7 ones, 25 ones, and then their star. All kind of concatenations. So this is regular. If you believe me, then can you build a machine that does this? Rogor. So the machine for the first one will be something like this, right? It will have 7 things like this. The machine for the other one will be a circle which has 25. How do you concatenate them?
2 accepting states.
Start state, where do you start? Start state has to be, you have to start somewhere, so it has to be unique. Where is the start state? So let's make it 3 and 2. So just for an easy example, think about 3 and 2. Accept states, yes, but start state, this is the machine that accepts multiples of 3. This is the machine that accepts multiples of 2. How do I build a machine that accepts 2 times I plus 3 times j? By the way, this is everything other than just one 1. But how can you do this? Where is the start state? Aka. This is the start state. Okay, let me just say one more sentence and we'll finish recording and then we can discuss this. So it's actually hard now. So it was easy to say that, okay, sometimes it's easy to build a machine, but sometimes it's easy to prove it mathematically. Okay, let's continue next time since the time is running out.